Pode iniciar.
Sim, sim, vocês precisam. Vocês vão ver, vamos discutir aqui e ver lá.
Fecha o microfone aí e fala aqui, velho. Não precisa falar microfone, só falar alto.
Então tá, o que eles vão estar enxergando?
Abaixa o volume do andar.
Beleza? Aí eu faço o processo normal. Agora. Tá me enxergando? Beleza. Agora, good morning for all. And, we are now together to start the PhD defense of Yasmin from the postgraduate program in chemistry from the Federal University of Santa Maria. This defense occurs in 4 steps. The first step is the presentation of the members to evaluate the work. The second step is when Yasmin will present your work. The third step is when the members, the referees, will answer Yasmin about the thesis. And the last step is when the referees stay together and all the people out, and the referees solve about the result. Okay? So the first step, Yasmin and me would like to thank you to the referees to participate. The referees are Professor Michael Badawi from Lorraine University, the Professor Luis Pinto from Federal University of Rio Grande, Professor Paola Azevedo from Federal University of Santa Maria, and Professor Mateus from Federal University of Santa Maria. The referees are composed of several areas. We have chemical engineering, we have chemistry, and a physician to better evaluate the work. Okay? Yasmin and me like to thank you for the members. Now we can start the second step. The second step is the presentation of the work by Yasmin. Yasmin, please.
So, good morning everyone. My name is Yasmin Vieira, and today I'll be defending my thesis named Planning Mechanistic Valves and Performance Amplification of Microwave Responsive Iron Copper Carbonaceous Heavy Structures in the Degradation of Pharmaceutical Substances. My advisor was Professor Dotto, and my co-advisor was Professor Zanella. So, due to the increase in the world population, which is estimated to reach about 8 billion people very soon and no longer to decrease, there is a high demand for industrial growth. And because of this industrial growth, we have the development of novel substances and compounds whose long-term effects are only now being studied. And followed by this, we have an increased disposal of wastewaters with these concerning substances. As the population increases, it is also observed the decrease of the access of people without access to safe drinking water. So, the increase in the number of these so-called emerging pollutants is of concern for the safety of the water in the future. Amongst these substances, we have pharmaceutical substances, which are widely encountered and consumed by over-the-counter sales, and the environmental occurrence of these substances can happen through the contaminated wastewater due to incorrect disposal, and through the consumption of these substances, which are then metabolized and excreted into the urban sewage system. So, either through contaminated wastewater or through extraction, these substances can enter the environment, causing environmental pollution. Because these substances are designed for biological purposes, they can interact with living organisms, which can lead to endocrine disruption effects. These effects are known even though the concentrations of these substances are relatively low in the order of nanogram or microgram per liter, because they are consistent and persistent. So these low consumptions are consistently being discharged into the environment, and we also observe an expanding pharmaceutical market worldwide, so no decrease in pharmaceutical consumption. Moreover, we know that the harmful potential of these substances can be amplified through bioaccumulation and caused by metabolic transformations or environmental degradation processes. Therefore, we have that the removal of these substances is of very importance, and nowadays the removal of these substances is consistently ineffective because the conventional treatments used in conventional water and wastewater treatment plants reach very low efficiencies, where the most common treatment methods are activated sludge or biological treatments, which can lead to only between 20 to 90% retained of these substances. So the pharmaceutical substances, because they interact with living organisms, they can deactivate the sludge or even kill the biological livings which treat this water, reducing the efficiency of the conventional methods. And for water treatment, we have the use of chlorine. But for chlorine, we can only observe in up to 50% of degradation of the substances and the production of chlorinated byproducts, which are enhanced in toxicity. So these substances, they re-enter the environment unaltered, and we have the indirect consumption through drinking water. Because this trend to increase consumption of pharmaceuticals and the increase in population, we need to update these methodologies for successful treatment, and the coupling of conventional treatments to new and effective methodologies aiming at these emerging pollutants is desired for study now. One example of these new methodologies are the advanced oxidative processes, which are based on the production of reactive oxygen species, such as radical hydroxyl, and these species interact with the organic pollutants, resulting in hydroxylated byproducts, elimination of functional groups, and side chain reactions. This will lead then to the formation of aromatic byproducts, ring opening reactions, leading to low molecular weight fragments, which are desired for easing the complete mineralization of these pollutants. When we talk about mineralization, we are referring to the complete conversion to carbon dioxide, water, and any inorganic salts resulting from different molecules in the structure of the compound. One example of advanced oxidation processes is heterogeneous catalysis, where a solid material is used as catalyst, easing the separation and the recycling of the catalyst, allowing its reuse. And one of the advantages of heterogeneous catalysis over homogeneous is the higher resistance to deactivation, fouling, and corrosion of the catalyst, because it is known that conventional catalysts are based in the use of metallic particles. One alternative to decrease the deficiencies in heterogeneous catalysis is the coupling of the catalysis to an energy assistance method, such as the use of microwave. And microwaves are an electromagnetic wave with a size ranging between 1 meter to 1 millimeter. And the use of microwave has been reported for environmental applications in microwave-assisted oxidation systems, homogeneous and heterogeneous catalysis, and for microwave-assisted or microwave-initiated photocatalysis. The advantages of using microwave in the systems is promoting rapid and uniform heating, the formation of hot spots, which are spots with much higher temperatures than in the mold solution, and synergic effects due to the imposed by the electric field and the magnetic field passing through the sample. As any other process, the use of microwaves imposes challenges, and the challenge here is designing catalysts specific for microwave-assisted applications. So the catalyst needs to be able to produce hotspots and reactive oxygen species simultaneously, while keeping structural stability, because when we work with microwaves, we are working under high temperature ranges. The literature then suggests the use of heterostructure or supported catalysts, such as the use of carbonaceous materials for producing hotspots or metallic particles to promote the reactive oxygen species. The combination of these two materials is proposed to enhance electronic flow and energy dispersion, optimizing the use of microwaves. Here we suggest the use of activated carbon because activated carbon has high surface area, it is highly available, easy to produce and modify, and it has good electronic mobility. In addition, the use of other order structures, such as multi-walled carbon nanotubes, which also have good surface area. They are also easy to modify. They present high electronic mobility at high temperatures, which is very interesting for microwave use. And they have a order structure. As a suggestion for the metallic particles, we present chalcopyrite, which has high symmetry, so it is a good candidate for applications under high temperatures, and due to its high symmetry, it is known as a zero gap catalyst, because despite its the variations allowed for this material, its band gap is considered very low. So, due to the complexity imposed by the interrelation between the factors and the parameters studied in this thesis, we divided our results into three crucial stages. So for the first chapter, we present the screening of local wastewater samples in order to know if the pharmaceutical pollution is already present and the viability of using microwave-assisted catalysis for the treatment of real wastewater samples. Then in chapter 2, we present the optimization of the degradation of a few pharmaceutical compounds, where we develop a new heterostructure based on the suggestions of the literature as a promising combination for microwave-assisted catalysis. And then in chapter 3, we fine-tune the degradation process, where we develop a microwave-responsive catalyst that addresses the structural problems revealed during the second stage. So for the first chapter, the journal article was published in 2021 in Science of the Total Environment, entitled Effective Treatment of Hospital Wastewater with High Concentration Diclofenac and Ibuprofen using a Promising Technology Based on Degradation Reaction Catalyzed by Zero-Valent Iron Under Microwave Irradiation. In this research, we collected wastewater samples in a local hospital in the northern region of Rio Grande do Sul, and we employed the microwave zero-valent iron system for the degradation after screening, and we chose zero-valent iron because it is easily found, it is easy to remove through co-precipitation, easy to reduce it, it has good cost effectiveness, and it has low toxicity. It is also known that zero-valent iron can promote ROS generation under microwave, and we tested this to know the viability for the degradation of the real sample. We characterized the zero-valent iron in order to confirm it was a single phase of iron, here as shown by the XRD analysis, and we also investigated the morphology of the material to confirm its characteristical spherical structure. Then the wastewater characteristics obtained show a high total organic carbon content, an even higher content for non-purgeable organic carbon, and a high chemical oxygen demand in this sample. We determined this by using TLC analysis, colorimetry for the determination of total phosphorus, and the ISO 6060 of 1989 for the chemical oxygen demand. Then the screening for defining the substances in the wastewater was adapted from Kovalova and Hernando using ultra-high liquid chromatography coupled to PDA or liquid chromatography coupled to tandem mass spectrometer. We were able to identify 16 substances and in the order of milligram per liter, which is relatively high. Then we investigated in the literature for similar reports where Santos showed that it is common for a load of 306 grams per day total of pharmaceuticals being discharged by a hospital with almost 1,500 beds. And by Wernicke, the amounts of 0.51 and 2.6 microgram per liter for diclofenac and ibuprofen. And here, the samples were collected from a hospital with 1,200 beds with over 3,700 employees. So the results are consistent and they worry because of the high concentrations for these 6 pharmaceutical substances in addition to the presence of all these others. Then we started to optimize the process by using preliminary tests, and we investigated adsorption, which was not expected, but we tested anyway to verify the zero-valent iron conditions. And we studied the variations of pH, catalyst dosage, microwave power, the maximum temperature, because we were working with microwaves, and the addition of hydrogen peroxide. The variables that significantly impacted on the process were only microwave power and zero-valent iron dosage. And we tested these item experiments by observing the reduction in chemical oxygen demand. The results pointed that the optimal condition was found around a microwave power at 780 watts, a zero-valent iron dosage of 0.36 gram per liter, and the natural pH of the sample, which varied between 4.1 to 4.7. The reaction kinetics followed a zero-order model for all the studied compounds, being for total organic carbon, total nitrogen, non-purgable organic carbon, and chemical oxygen demand, and for ibuprofen and diclofenac. This is common when we have a medium that is really concentrated, so we are not able to see differences in the reaction order for any of the compounds. We then studied the possible pathways for diclofenac, and we observed similar patterns than the literature reports, and for ibuprofen in the same patterns. So our conclusion from this study was that the optimal conditions were using a considerably low microwave power at 780 watts, and conventional oven uses about 1,200 watts, the catalyst dosage of 0.36 gram per liter, and the natural pH between 4.1 to 4.7. The transformation pathways identified were consistent with the ones found in the literature for other catalytic processes, so we did not produce any other recalcitrant byproduct than the ones already reported. The use of the microwave-assisted catalysis using zero-valent iron as catalyst is effective for removing the high concentrations of total organic carbon, total nitrogen, and chemical oxygen demand within 60 minutes. And the complete removal of the target pollutants molecules in the study, ibuprofen and diclofenac, occurred within 35 minutes. So our remarks in this study and perspectives is that the local pollution by pharmaceutical substances is indeed ongoing. The microwave-assisted catalysis is promising for the treatment of real wastewater, and no different fragmentation patterns were found. So this process does not increase the toxicity of the final sip. Then in chapter 2, we proceeded to test the development of novel catalysts, and we designed a catalyst based on chalcopyrite/activated carbon, forming a heterostructure as a microwave responsive catalyst for reductive and oxidative degradation of ibuprofen, ketoprofen, and diclofenac. This study was published this year in Chemical Engineering Journal. So, by knowing that microwave can interact with carbon sources to form hotspots and degrade contaminants and micromolecules, we observed that in the literature, some results were already showing high mineralization rates within 1 minute for oxytetracycline, and the possibility of reduction reactions under microwave assistance. So we produced the heterostructure, and here through XRD we confirmed the stability by the addition of the amorphous structure to the crystalline peaks. The same patterns for the FTIR analysis. The surface area of the activated carbon decreased after we added the chalcopyrite nanoparticles. And most interestingly, we observed its high stability in up to 750 degrees during the thermogravimetric analysis, with a decrease of only 15% of the mass of the catalyst during this increase in temperature. And the decrease in the band gap, which decreased from 2.86 electron volt to 1.33 electron volt for the catalyst, showing an enhancement in electronic properties. During the scanning electron microscopy, we were also able to see an even distribution of the particles here in white over the surface of the activated carbon here in black, and the appearance of the copper and iron elements on the sample, which did not occur for the carbon sample only. We investigated the reaction kinetics for all the pollutants we studied, and the kinetic for ibuprofen fitted best for the pseudo first order model, and the kinetic rate observed was superior than those reported for conventional systems such as ultraviolet and titanium dioxide, and using hollow lanthanum ferrite peroxide, where we observed that our catalyst was able to degrade faster, over 10 times more pollutant, and with 1/4 less catalyst needed than the ones reported in the literature. The recyclability for ibuprofen degradation was also high, being observed no significant decreases in the kinetic rate in up to 10 cycles. For ketoprofen, the outcome fit was also for the first order model, and the recyclability was even more stable for this compound, and the degradation, the total mineralization was reached within 30 minutes, as the literature reports the need for approximately 180 minutes using even the so-called advanced catalysts, such as the ones doped with titanium and using graphited carbon nitride, or catalysts with higher cost, such as using silver. For diclofenac, the pseudo first order model also represented better the process. Here we can see a higher decrease after the third recycle, but shown stable after the fourth and fifth recycle. And in this study, we were able to mineralize diclofenac 100% of the concentration tested after 30 minutes, while the literature reports approximately 62% and 65% after 3 hours and 6 minutes using other catalysts. As we knew that our catalyst was able to produce several recycles, we tested its structural stability by investigating the leaching of the metallic particles loaded into the material. So we used atomic absorption spectrometry to measure copper and iron content, which resulted in less than 2% leaching of these metallic particles from the catalyst, and we observed an increase in the amorphous phase for carbon, but without losing the crystallinity of the chalcopyrite particles in the 10th recycle, which corroborates with the structural stability of this material. Then we also investigated the degradation pathways for the pharmaceuticals studied, because this can point to possible mechanisms occurring by the catalyst. So here we observed sequential hydroxylation consistent with the formation of radical hydroxyl. For ketoprofen in slower rates, the same process as ibuprofen, and for diclofenac, we were able to confirm the forming of 2 reductive fragments, which corroborate with other pathways possible. Then we used quantum chemical calculations to estimate the reactivity of these fragments, where we show that for ibuprofen, the conversion of A1 to A3 was more favorable, and the subsequent degradation was slower in this pathway. So when the pristine molecule degrades to A3, the pathway tends to slow down. And when A1 converts to A4, it can convert to A5 and A10 directly. So the mineralization here is faster, with an increased reactivity when compared with these 2 first fragments. For ketoprofen, as it was observed a slower fragmentation by the removal of terminal ramifications of the molecule, we saw the possibility of forming fragment B4, this one here, directly to B2 or B5. So here there was no no significant variations in the kinetic rate over the reaction. And for diclofenac, the route that evolved from fragment C3 was possibly dominant over the other proposed pathways, because here we see a very high increase in electrophilicity for this molecule, much higher than for any other compound reported. And as radical OH is formed, it would preferentially interact with this compound, leading to faster mineralization. And the formation of the fragment C10 and C11, which were the reductive fragments, were observed only during the first minutes of reaction. So, as these fragments were no longer formed, the reaction speed increased. In order to confirm the surface phenomena, we tested different concentrations of the pollutants and fitted them to the Lagrange-Michaud equation model, and we observed a higher fit for diclofenac, which was precisely the one that showed a possible interaction with the surface. And we tested the Ross scavengers, which are added to scavenge these possible reaction sites on the surface of the catalyst. When we added EDTA, we observed that the reaction almost stopped. It was a dramatic effect, suppressing the reaction by hindering the acidic site, so the electronic flow. And we saw that the mechanism was highly dependent on the formation of electron hole vacancies. And the electronic charge mobility by the formation of hydroxyl radical was also confirmed by the addition of isopropylic alcohol, which decreased the kinetic rate approximately 10 times. So we proposed a general mechanism for the catalytic degradation of these three substances on the surface of the ACFS heterostructure, where the decomposition of hydrogen peroxide formed radical OH enhanced by hotspot formation, so here the first possible mechanism occurring, then the catalytic oxidation by the attacks made by the radical hydroxyl, and the catalytic reduction due to the electronic flow on the surface of the material. Our conclusions are the observation of three distinct mechanisms which show the versatility of the catalyst, that the kinetic rates obtained were superior to those reported for other catalytic systems, and that charge transfer phenomena improved the effectiveness and recyclability of the heterostructure when compared to pure chalcopyrite. Our remarks and perspectives on this study is that it is possible to promote oxidative and reductive routes under microwave radiation. The catalyst is versatile and robust. It has high recyclability, and that charge transfer and charge distribution is the key to optimize the process. In the last stage of this thesis, we then developed a novel catalyst, and we studied the catalytic behavior of multi-walled carbon nanotubes loaded with chalcopyrite nanoparticles during microwave-assisted degradation of acetaminophen and naproxen. This study is under finalization for soon to be submitted. Here then, we tested the hypothesis for the use of more ordered carbonaceous structures, as the literature reports that the loading of metallic particles to multi-walled carbon nanotubes can increase electronic conductivity by approximately 20 times. So then again, supported by this theory, we synthesized this catalyst and we showed the successful coupling between these two materials, preserving the graphitic phases of the multi-walled carbon nanotubes on the preceding sample, shown here. The same patterns for preservation here in the FTIR analysis, a decrease in the surface of the multi-walled carbon nanotubes by incorporating the chalcopyrite particles, and the most significant analysis here was the band gap analysis, showing a decrease from 3.13 electron volt to 1.98 electron volt in the copper. The carbon nanotubes used in this study were synthesized by our group, employing microwave-initiated combustion of cedar fuels residues, and here we proved the successful formation of these nanotubes. And then we analyzed, similarly in the than in the last study, the forming of pure carbon for the sample, and that the addition of the chocolate grid here caused these particles to repel themselves. And then we show an even distribution and the appearance of copper and iron elements in the sample, as well as a decrease in carbon content after the incorporation. We optimize the reaction conditions, testing the microwave power, the catalyst dosage, and hydrogen peroxide addition. Being found that the optimal condition here was the use of 0.5 gram per liter of catalyst, a microwave power of 500 watts, even lower than the ones we tested before, and the hydrogen peroxide dosage of 50 microliters per liter. So with these conditions, we investigated the pH effect, and it was found that in pH 5, the kinetic rates increased much more than for any other pH value. Then we tested the synergy between these parameters by means of analyzing the total organic carbon removal. So we tested a system where we only used microwave and hydrogen peroxide with no catalyst. Then we tested the novel catalyst with microwaves without hydrogen peroxide, the novel catalyst with conventional heating and hydrogen peroxide, the proposed system with the novel catalyst, microwave heating and hydrogen peroxide, and we tested the pristine multi-walled carbon nanotubes. So here it is possible to see that there is a clear synergistic effect occurring between the use of these three variables in the optimized pH. Then, as we conducted the experiments, we observed through liquid chromatography and through TOC analysis that the reaction speeds was different. So we investigated the fitting of these reactions to the kinetic models. All of them were better represented by the pseudo first order, which indicates the collaboration of the reactive oxygen species. But here we were able to observe this interesting phenomenon for the differences in kinetic rates for molecular structure degradation, which I mean by the degradation of the pristine structure, and for TOC removal, which is the conversion of the fragments to carbon dioxide and water. So we fitted this again for different pollutant values for the Laminar-Mitchell reaction, and this showed that the molecular structure degradation was not so reliant on surface phenomena as the TOC removal was. Then we investigated the recyclability, and here, by changing the activated carbon to multi-walled carbon nanotubes, we were able to increase the recyclability of the catalyst from 10 to 20 stable recycles. And even though the kinetic rate decreased, we were able to totally mineralize the compounds if we extended the reaction time. So here we see similar patterns for molecular degradation and for TOC removal with differences only in the kinetic rates from approximately 0.4 to 0.3. We also investigated the stability of the materials using scanning electron microscopy. So here we did an elemental mapping of the sample, and we showed that both copper and iron still remain on the sample after 10 and 20 reuses, with no significant differences, as we expected through the leaching analysis. We also investigated the plausible degradation pathways for acetaminophen and for naproxen, and we studied these using quantum chemical calculations. So we observed that for the most plausible routes, according to the values estimated for reactivity, that the fragment ACT1, which is the pristine molecule for acetaminophen, suffered from reactive oxygen species attacks, leading to its hydroxylation, a successful decarboxylation of the fragment, then the combination of reactive oxygen species and electron charge mobility for its mineralization. And for naproxen, similar pathways, so first hydroxylation caused by the formation of radical hydroxyl, then ring opening reactions, and the final mineralization by using, through the electronic charge transfer phenomenon. now we have optimized the process, we wanted to confirm its environmental applicability. So we studied the common ion effect, where we tested for various ions present in the environment, and we observed a rate decrease of approximately 35% for the formation of basic salts, where we see that there is a possibility for radical OH being converted to radical species of these salts, for these carbonate salts, which have decreased oxidative potential. And we also saw that there is a possibility for these other salts to interact with the surface of the iron of the catalyst and forming a sort of complex precipitate. Here, because we are working with multi-walled carbon nanotubes, it is also very important to study the toxicity of the treated effluents, because we know that nanotubes have increased toxicity and we are not totally aware of the possible effects caused by them, because we do not have total control, because they have very small sizes. So we carried out phytotoxicity assays for lactuca sativa, which is common lettuce seeds, and we observed that after the treatment using the novel catalyst under microwave radiation, the germination growth was nearly similar to total as in the control sample, and the root elongation was also very similar to the control group. As before the catalysis, nearly almost no seed germinated. The ones that did not grow even half the expected for the control group. At last, we carried out another theoretical analysis for the fragments studied. So we conducted an EcoSAR analysis, and here it is important to notice that we studied the final fragments, which were the ones which could possibly be present in the wastewater in the final stages. And we observed here that the value for acute toxicity for fish, definite and green algae, as well as for chronic toxicity, increased from ACT1 to ACT10, which is good because it means that we need more concentration of these fragments to cause a significant effect than in the initial one. And for naproxen, the effect was even more dramatic by decreasing by many times the amount needed for the final fragments in comparison to the pristine molecule. Our conclusion from this study is that we were able to obtain really high kinetic rates with total mineralization of acetaminophen and naproxen after 12 and 16 minutes. Two distinct mechanisms for the degradation of the pristine molecular structure and mineralization occurred. We observed that the formation of the radical hydroxyl contributed more to the degradation, while the electron hole pairs were active towards the mineralization. The degradation routes also produced degradation byproducts less toxic than the original molecules studied, and we saw a high recyclability of the composite in up to 20 reuse cycles. Our remarks and perspectives are that the ordered structure of the multi-walled carbon nanotubes increased the efficiency of the microstructure when compared to AC, and that increasing stability relies on the perfect match between the electronic parameters between the blended materials. So, our conclusion from this thesis is that the key to control the stability for microwave responsive catalysts is the fine-tuning of morphological and synergistic attributes related to reactive oxygen species generation and hotspot formation by using ordered carbonaceous materials. Thank you very much for your presence. I thank my committee for their time and their evaluation. I thank my advisor, Professor Guilherme, the Federal University of Santa Maria, the graduate program in chemistry, and CAPES for the scholarship. Thank you very much. I'm available for questions.
Well, now we go to a break or no? Short break, okay. A short break of 5 minutes, okay, for a back or as you want, okay. And then we start the third step, okay. That is the documentation of the SME and the questions. Okay? 5 minutes.